Okay, so we're going to look at how to solve ODEs using Laplace transform. We're going to pick some examples from here to help us evaluate. Okay, so what do we need? Now here, if you have a differential equation, and in this case, we're saying it's based on some function f of x. Now, the function itself, f of x, must be differentiable, and the derivatives have to be piecewise continuous. So it has to be continuous, so it must have continuous derivatives. When you differentiate, the response should be something which is continuous. Now, based on that, so it means that you can get the first derivative, you can get the second derivative, and it will still be continuous. You can get the third, and so on, until up to Fn. So this is possible. Now, if you can get all these derivatives, and all these derivatives would turn out to be continuous functions, and the function itself, Fn, is going to be a piecewise continuous function, then we can use the Laplace transform on the function. So here we have the Laplace transform of f of n. So basically, this is the derivative, the nth derivative of f of x will be equal to. So in this case, this is all you need to understand. This is a differential. Now, since the Laplace transform of a differential here is going to be equal to, we're going to have s to the power n. So power starts with whatever this is. And then we have its Laplace. And then minus. Then what follows is going to be exactly what we have here, but this starts changing. So this reduces to s to the power n minus 1. And instead of the transform there, instead, what we're going to have is going to be f of 0, the original function, but substituted with a 0 there. Then minus. Next, again, the power now reduces by 1 again, becoming s to the power n minus 2. But now we'll have the first derivative of the function at that same point, 0. And then we keep on going with this. So we'll keep on going with this until we are done, until when we have, until when the value of n here, the n derivative reduces to 0. So what does this mean, and how does it look like when you're trying to solve a problem? Take, for example, you wanted to get the transform for y to the power, or the first derivative of y. So if you're doing it for the first derivative of y, what do you get here? So as you can see, first you have s to the power whatever the derivative number here is. Here the derivative number is 1, so this will be s to the power 1. And the first term always multiplies f of s, or fs. So based on this, this is going to multiply fs. Then minus what follows. The next part is going to be, see, we're reducing the powers for s. So we're supposed to have s to the original power n. N was 1, so this is going to be 1 minus 1. But 1 minus 1 is 1. So in this case, there's no need to keep this since it will be a 1. But what follows? Here, it has to be whatever this is at the point 0. So basically, this is what we get. And if you had, or if we were looking for the transform of the second derivative of y, how would it look like? So now the derivative number is 2. So this will start from s to the power 2. And then we have fs there. Then minus Now the power reduces by 1, so 2 minus 1 becomes 1, so it will be s to the power 1. And then what do we get next? F will be to the power 1 first. So we're going to have f to the power 1, or not to the power 1, the first derivative, not even the first, yeah, not the first derivative, just the original function, f of 0. Then minus, when we now go for s to the power n minus 2, in this case, since n is 2, it will be 2 minus 2, which will be 0, and s to the power 0 is going to be 1, so we might as well not write this. Now we'll have the first derivative of f at that point. And recall that here f is y, so I might as well not write f, I just put y here. So this is how we transform a derivative. Now, here's something to just help us understand what we're doing. Suppose you have a differential equation, the second derivative of y minus the first derivative of y plus y is equals to 5t. And then here, this is an initial value problem. So what this means is they'll give you the initial values of the function y. So when t is equals to 0, y is going to be equals to -1. And when t is equals to 0 again, the derivative of y is going to be equals to 2. So to work this one out using the Laplace transform approach, what do we need to do? So we're going to transform the entire expression. So if we're going to transform this, notice that we'll have to get the transform of this, the transform of that, of this, and of that. So how is it going to work? So when we get the transform of y to the power 2, what are we going to have? So not y, I keep saying y to the power 2. That's the second derivative of y. So we need to get the transform of the second derivative of y. And then we need to get the transform. 10 is a constant, so we can bring 10 outside. We need to get the transform of the first derivative of y. 9 is a constant there, so it will come out. Then we need to get the transform of y. And on the right side, 5 is a constant, so it can come out, or we can keep it there, doesn't really matter. But we'll have to get the transform of t. Now, in dealing with these transforms, it helps a lot when you have some of these memorized, say the transform of when you have t to the power 1, what would be its transform? When you have t to the power 5, what would be its transform? You don't always want to start getting these transforms from scratch. You waste a lot of time. So if you can memorize the most commonly used ones for exponents, trigs, and so on, it would save you a lot of time. So let's start with the second derivative of y. So as we just showed earlier, when getting the second derivative of y, what are we going to have? This is second derivative, so it starts with s to the power n, the power 2, I mean. And then this multiplies fs. So here, the fs which we are having here, it's basically going to be the transform itself, the overall transform solution that we're looking for. So we can keep it as fs, so I can go with ys. So eventually we would have to make this the subject of the formula. That is what we'll have to do. So, but remember how we transform the second derivative. First, we go with s to the power 2. This one comes with the transform. Then after that, minus. Now we reduce the power by 1. So this is power 2 equals to power 1. But now we don't use ys anymore. Instead, what is going to follow is going to be the function y itself at that point 0, at the initial point. Next, minus. Now we're supposed to go to s. The power for s reduces by 1. So since it was power 1, here it becomes power 0, since it will be 1 minus 1, which is 0. So it will be s to the power 0, which is just 1. But y will now get the first derivative of y at that point. Once we reach s power 0, then we're going to end there. We're done getting the transform of the second derivative. Now we come to the transform of the first derivative. The first derivative starts with a minus 10 there, so we'll have the minus 10 in position. Now we need to get the transform for the first derivative. In the same way, it will start with s to the power. Since it's the first derivative, the power here is 1. And I've gone for ys and not fs. So I'll have y here with an s. Next, you remember what comes next. We're subtracting here. And then we're going to have s. S here had power 1, so it's going to be 1 minus 1, which is 0. So it's going to be s power 0, which is just 1. So we won't write that s, but instead we'll have y at the initial point, y0. So I hope you're seeing the trick on how it goes. When you have the first part, the other parts are going to be subtracted out. And you start with y, the function itself at the initial point, then the derivatives just like that, depending on how far you have to go. So that sorts out this. Now we go to 9 and multiplying the Laplace for y. So you have plus 9. Y there is, it's not a derivative there, so we're not differentiating it. So what would be its transform? So in this case, when we're not differentiating here, what are we going to get? It's basically the same thing that we're looking at here. When we're differentiating, when you had the second derivative, s started with power 2. When we have the first derivative, s started with power 1. So when we don't have a derivative altogether, so it means that this is the more like 0 as the derivative number. It's like s already starts with 0. So we're starting with the last one, basically the one that ends there. It's going to be s to the power 0. And remember, the first one that we always start with is the one that comes with the ys. But s to the power 0 is just 1, so you might as well not write this one here. So this concludes everything this side, leaving us with only what to do on the right-hand side. Any questions up to this point?
Maybe can you just go through the first one, why the derivative of what?
The
second derivative of what?
The Laplacian for the second derivative?
Yes.
Okay. So let's do a bunch of them to just make sure that you get how it goes. Suppose we wanted to get the Laplacian for the third derivative of y. So if we wanted to get the Laplacian for the third derivative, so I think we did the first two, so I might as well do the third. So if you're going for the third derivative, you start with s to the power 3. Then the first one will get that y function of s. Then minus, you always subtract here. If s started with power 3, the powers of s will be reducing until when you reach s to the power 0. Then you stop. So the next thing is going to be s to the power 2. But the only one that carries s, a ys, is the first one. The rest will carry y of 0, the initial value of y. Then secondly, observe that the first term here, among the ones subtracting, you do not, it's not a derivative, it's y itself at the point 0, or at the initial point. Minus, from s to the power 3 to s to the power 2, the next one will be s to the power 1. And again, the ones we are subtracting, they come with y. But here, y was not differentiated at all, so it was like 0 as the derivative number. Now we differentiated once at the initial point again. Remember, we have to keep doing this until when we reach s to the power 0. So s to the power 3, to the power 2, to the power 1. So we still have one more. Minus s to the power 1 minus 1 becomes s to the power 0. And then this will be y. Look at y. Here, y is 0, y is power 0, or y differentiated 0 times, y differentiated once, so the next one will be y differentiated twice. So since we've reached the term that has s to the power 0, that is where we will end. To make sure you get it, let's do y, the fourth derivative of y. So let's see if you've got it. The first one will start with what?
That is 4.
Yes, to be s to the power 4. So s to the power 4 multiply what?
5 by y, please.
Ys. Then
S to the power 3.
s to the power 3. Yes.
5 by 5, 5 and 0. 5 to the power 2 and 0.
Yes.
Minus s starting with s1.
Remember s4, s3. What comes next?
S2.
S2.
Then y starts increasing there, not so?
Yes, that y starts increasing. So I will go to what? To 1, right? So y starts from 0, then 1. Then we have s1. Y goes to 2. Then the last one is when s has 0. You always go up to s has 0. So I have minus s0 y3. Have you got that?
Yes, yes.
This is what is generalized in the statement we had at the beginning to say the transform of a derivative, let's say y to the power n. The transform of this will be equal to s to the power whatever this derivative is, derivative number is, multiplying ys. Then minus s, now the power reduces by 1, and then you have f0. Then minus s, the power reduces again, and then now you have f prime. And then minus, this will keep on happening until when you reach the term where you have s to the power 0. And then this one for s to the power 0 will have f to the power n minus 1. Not the power, that's a derivative number. This will always be the last term. Look at the characteristics for the last term. The derivative number is always 1 less than n here. Secondly, the power for s is always 0 there. That will be the last one in this continuation. Have you got it?
Yes, yes.
Yeah. So with that in mind, we continue with the expression that we're dealing with. we had grown up to that point. So the only thing that was left here is the right-hand side. On the right-hand side, we're looking at the Laplacian for a variable t. So if you recall, we had actually derived the Laplacian for t to the power 1 in our other class. I think you were not there. I think the other guys were there. But we had derived that. Do you know the Laplacian for t to the power 1?
Into 1 over s.
Okay, so it's 1 over s squared. So here we're going to have 5. Since remember 5 was outside. And then 1 over s squared. So these ones you have to know them, at least the basics. So that will be the Laplacian that side. Once you're done with this, just simplify the expression. Your solution, which is basically the transform, will be ys. And since ys here appears in several places, you want to group it so that it appears on one side. It becomes plus 10y plus 9ys is equals to 5 over s squared. So this is what we now have. But recall, this was an initial value problem. We were told what y0 is. y0 is minus 1. Y prime 0 is given as as 2. So when you're dealing with an initial value problem, they will tell you the value when t is 0. They will tell you the value of even the derivatives. You'll be told what they are for t is equals to 0. Implying that if you are dealing with a transform which had to do with a third derivative, they will tell you the initial value for y0. They will tell you the initial value for y prime 0, the initial value for the second derivative of y as well. You'll be given what these are, unless if they're the ones they want you to find. So here they're saying that y0 is -1, is it? Yes. And y prime 0 is 2. So we can make those substitutions and see what we remain with. So we have minus, this is -1, so to make this plus, and this will just remain an s. Again, that's a derivative, so that will be minus, that's a 2, minus 10 s prime ys, then plus again, that's y0. y0 is -1, so you have minus 10 here, then plus 9ys. So here what you have to do is isolate ys. So everything else can go to the right side. I don't want to deal with the denominator there, so I can multiply through by that denominator s squared, and then I'll do the isolation. So if I multiply through by s squared, now I'll have s to the power 4 in the first term, and then I'll have, I'll start isolating. When this will multiply s squared, okay, I'm seeing s with the prime. That's not the prime, that's s to the power 1. So since that's power 1, remember s is not differentiated, s comes with the powers. So no need for me to write that prime there, just power 1. So in the s power 1 multiplies s power 2, we'll get s power 3. So this is minus 10 s power 3 ys. I see another ys showing up there. To multiply s squared, giving us 9 s squared ys. Everything else goes on the right. Just don't forget the ones which are already on the left have to multiply s squared. And that's those three. If you say I've left something, please to just point it out. On the right side, 5 already was there. S, this s here, multiplies s squared to become s to the power 3. It was positive, so it becomes negative. The 2 and the 10 will combine, they're both negatives to give us minus 12. The minus 12 crosses to go to the right of s. Let's say the minus 12 multiplies the s squared to become minus 12s squared. When it crosses, it becomes positive to become plus 12s squared. So this is now what we have. Our goal is to isolate ys on the left side. So ys, which is our transform, is now here. What remains is going to be s to the power 4 on the first term, then 10s to the power 3 on the second, then 9s squared on this third term. Is equals to 5 minus s plus 12 to the s to the power 2. So this is now our expression. From here, we see that ys is equal to 5. I can actually start with the squared one. Or, yeah, that's right. Minus s to the power 3 plus 12s to the power 2 plus 5 over, then we have s to the power 4 minus 10s to the power 3 plus 9. So this becomes our expression. So we just have to make sure. Yeah.
Question there. Is it not 9s squared? The denominator.
9s squared, yes. Yeah, that's 9s squared. Okay, so here we just want to make sure that we haven't made any errors to reach this point. So if there are no errors, then we can proceed to look at what comes next. Another thing that you just want to be conscious of here is, or just keep in mind, is that every time when you're using these methods to solve, the continuation on how to solve these expressions will mostly end up being something that you can solve, or something you have to continue by getting the partial fractions. Yeah, you definitely have to go the partial fraction approach afterwards. So when you reach this stage, you want to start working towards those partial fractions. How are you going to get these? You'd have to factorize the polynomials that you're dealing with and see how best to represent them. So that is what you'd have to do here. So let's see. How can we puzzle this one out? Okay. So for simplicity here, you see that the expression you have in the numerator, the first part has s, second part has s. In the denominator, everything has an s. It's only the 5 in the numerator that does not have an s. So in order for us to get the partial fractions easily, I don't want to start getting polynomials for s to the power 4. That is going to be a little bit longer. So to avoid doing that, I'll split this into 2 fractions. So I'll get the numerator, which the parts which have s in the numerator, s to the power 3 and 12s squared. I'll give them this. In the same way, since I'm splitting this into two fractions, the other fraction has to be 5 over s to the power 4 minus 10s to the power 3 plus 9s to the power 2. This should make sense because we know if I have a over, let's say, x, maybe plus b over, say, y. To write this as a single fraction, we know to say, not this, let me say same denominator, x. As a single fraction, same denominator, this is the same as just the common denominator, which is x, and then just add the numerators. So this is what I've done. I've just said, okay, probably these are the two numerators which were being added. They're being added because the denominators were the same. So that is what I've done there to reach that stage. Once you're in this position, now you see that the first fraction can easily simplify since s is common throughout. In fact, s squared is common throughout. When you divide through by s squared, you remain with minus s on the first part. You remain with 12 on the second part. And then in the denominator, you have s to the power 2 minus 10s. Then here you have plus 9. For the second fraction here, there's really nothing we can do except recognize that here s squared is a factor in the denominator. So we can perhaps factor it out, s squared. What remains is going to be s to the power 2 minus 10s plus 9. Now look at the expressions we have. And remember I said we need to come up with the partial fractions. But we wanted to find the easiest way to deal with the partial fraction. If you had to come up with partial fractions for something like this, it would take you longer to find those partial fractions. But look at the way we've simplified it in this form. We now just have to factorize a quadratic expression, which is easier than dealing with s to the power 4 in the previous expression. And here, of course, we can think about trying the product and sum to factorize. The product will end up being 9s squared. Two terms you multiply, they give you 10. You multiply, they give you 9. You add, they give you 10. That has to be a 10 and a 1. A 10 and a 1. So they have to add to give you negative 10. So both have to be negative. So when you add, sorry, not a 10 and a 1. That's a 9 and a 10. When you multiply them, they'll give you 9 positive. When you add them, they give you negative 10. Once you have those, you know to say that then the first fraction, I'll start at the positive part, minus s. And then the two fractions, when you, no fractions, the two factors, when you factorize this, it will be s minus 9, and then s minus 1. Then plus the second part here, 5 over s squared. Since this is still the same quadratic equation, quadratic expression, it will also factorize the same way to give you s minus 9 and s minus 1. So this is our ys. Now getting the partial fractions is a little bit easier. Since we're able to factorize, we can proceed with getting the partial fraction. Any questions up to where we are?
Yeah, me too. I'm following.
So let's get them one at a time. Let's get this one first. So to get the partial fractions for this one, we know to say if you have linear coefficients, the partial fractions will have a constant a over the first factor, not linear coefficients, linear factors, over the first linear factor And I hope you don't get confused. This is S not 5, that is a 9. And then plus another real coefficient there in the numerator, and then over the second factor, S minus 1. So now all we have to do is find what A is, find what B is. As a single fraction, we have A. This will have to multiply that, which is S minus 1, plus B will have to multiply this, which is B, S minus 9. Over the denominators will multiply S minus 9, S minus 1. Now, at this point, the denominators are the same, so it means that even the numerators have to be the same. So we have 12 minus S is equals to A, S minus 1, plus B, S minus 9. So we have this. Solving this should be relatively straightforward. We want to find A and B. So we're going to be strategic here. Mostly you can pick any values. S is equals to 0, S is equals to 1, S is equals to 2, and so on. But here, we'll pick them strategically, knowing that if S is 1 here, we can find B. And if S is 9 here, we can find A. So let's start with S is equals to 1. If S is 1, the expression reduces to 12 minus 1 is equals to, this will be 0 if S is 1. So remaining with only B, 1 minus 9. This is going to be 11 is equals to, this part will have 1 minus 9, which is minus 8. So I have minus 8B. So that is what we have there. So I hope that that part is okay.
Yes. So here you're saying that we could pick any number.
Yes, you can pick any number, yes.
Or usually one, yeah, or usually 1 and 2 can still be good.
Yes, yes.
So still, even if I pick 2, I will still find the same value.
Even if you pick
different.
Yes, even if you pick 2, you still find the same value.
Huh? Okay.
The only thing is, it will just take you longer to solve.
So, okay, yes.
So, we have this, and then when you solve this to find B, we're getting B is equals to 11 over 8 with a minus there. Okay, so that is what we have. See, another way we could have actually approached this, which is perhaps even more efficient. Because here, if you look at what I was doing, I was approaching this by factorizing this, and then I'll say whatever I have here plus what I'll get this side. If we did not want to do it this way, another method that we could have used, which is perhaps more efficient so that we don't have to worry about coming to add them, is to combine this and look at them as one whole thing, then get the partial fractions for the whole thing. The idea of dealing with them like this was so that we can easily factorize. Wait, I want to use the factorized ones already. Factorizing was the key part of dealing with them separately. Because if you had not factorized, you'd have been forced to deal with a polynomial of degree 4, which would be more difficult to factorize. But having factorized and then you're in this form, you can easily combine them. Above all, they do have similar, the denominators are similar there. The common denominator is actually going to be this one here. So we can get that and keep it here. Now, when you use, all we're doing is making a single fraction now. This denominator divides here Notice that what will remain will be s squared. So s squared will have to multiply the 12 minus s. Plus, when this denominator now divides here, the response will be 1. So 1 will multiply 5. Observe that now, after combining the two fractions, what we have is s squared multiplies 12, we get 12 s squared. 5 multiplies s squared, we get, so this is not, yeah, that's 12, okay. This is not 5. That's what I wanted to point. That's not 5. I confused myself. My s, remember that's an s. Otherwise, if it was a 5, I would have subtracted a long time ago. So s squared multiplies s, not 5. It becomes s to the power 3. I hope you followed that one there.
Yes.
Okay. Then over, in the denominator, we have s squared, s minus 9, s minus 1. Okay, so the earlier approach we were using here, which one was that? Here. We wanted to get the partial fractions for this one, which we had started doing since we already obtained b. So would have also done s is equals to 9, so that when I use s is 9 here, I have 9 minus 9 to give me 0. That would have given me 12 minus 9 is equals to a. 9 minus 1 would have been 8. So 12 minus 9 would have been 3. And I've had a is equals to 3 over 8 as my a. So the first part, just this part here, the partial fractions would have been, remember it's a, and a was coming out as 3 over 8. Would have had 3 over 8 over s minus 9. Then plus b over s minus 1. So it would have been minus, since b comes with the minus, so minus 11 over 8 over b had s minus 1. This would have been just for this part. But to finish it up, you'd have been forced to also do the partial fractions for this part as well. Then add them. Observe that this part as well will also have s minus 1, a fraction that will have s minus 1. So you'll be forced to add that fraction with this one since they'll have the same denominator. In the same way, it will also have a fraction that will have s minus 9 in the denominator. That one would have to come and combine with this one here to make one fraction. So this approach might seem a little bit too much since you have to come and combine them again. So instead of that, we have this approach that we're trying to deploy now, where before getting the partial fraction, first we combine those two fractions into 2, then move on to get the partial fractions. But either approach works, either approach is fine. Which approach would you want me to finish to the end?
I think let's see the one that you're doing, the one that is more direct, so that we see where it goes.
Okay, so we do this one?
Yes.
Okay. So if we're getting the partial fractions for this one, what factors do we have here? I see linear factor, and what factor is this? Quadratic. So if a quadratic factor is involved, it starts with the same factor to the power 1. So if this was maybe s minus maybe 2 to the power 2, it means that the first one that would have started would have been s minus 2 to the power 1. The second factor, so this one, the coefficient is going to be a real number a. So don't confuse this a to the one we used earlier on. Here we're finding a different value. Then plus, we're still with the quadratic. The quadratic, you have to go up to s to the power 2. Meaning if you were dealing with this one here, you'd have had A here, the next one would have been B over the same factor, S minus 2, but now it would have been to the power 2. This is a quadratic factor. We deploy this approach of getting partial fractions when you're dealing with a repeating factor. Let me not say quadratic factor, but instead repeating. When you're dealing with a repeating factor, this is when you do first the same factor, S, next, S squared. If it was repeating 3 times, we'll do first over S squared, then over S to the power 3. That is if it is repeating 3 times. If it is repeating 4 times, we have to do S to the power 2, S to the power 3, then finally S to the power 4. That is for repeating factor. The treatment of quadratic factors will come later. So here, we are interpreting this as a repeating factor. Okay, so we're coming up to B over S squared. So we have handled the repeating factor. The next factor we have is S minus 9. It is a linear factor, so that is S minus 9. And it's a linear repeating factor, so it will be powers over numerator C there. Then we also have another linear factor. So we have S minus 1 there. So, and in the numerator, we're just going to have some real number D. Now, I should point out that if this was a repeating factor but quadratic, it would have looked a little bit different because we would have had to employ the approach for quadratic factors. Remember, quadratic factors, it's A plus BS, if that's quadratic. But since you would say quadratic repeating, then we'd have to do both the quadratic and the repeating part. But again, you found a question like that under transforms, then it would definitely take a lot of time. So here we now just have to find A, B, C, and D for us to complete our idea. And to do that, we'll start by making this into a single fraction on the right side. So if we make the right-hand side a single fraction, of course, we can say multiply the denominators, or we can get S squared. If you don't want to stress, you can actually just get this, because obviously the denominator will always be the same as that. So get S squared, S minus 9, S minus 1. So just get this as the common denominator, because everything here, we will be able to go or divide through that. S, for example, can divide into this. When S divides into that, what will remain is going to be A, and then you have S, but you still have S minus 9. You still have S minus 1. When A squared divides here, it will cancel with the A squared, with the S squared. What will remain will multiply B, so we'll have plus B, and then you have S minus 9, and then you'll have S minus 1. That is what will remain. And in the same way, when S minus 9 divides here, hope I wasn't saying multiplying, divides there, it will cancel with this. What will remain will multiply C, so we'll have plus C, and what remains, it will be S squared, and this multiplying S minus 1. In the same way, when S minus 1 divides there, what will remain? Multiply D, so you have S squared multiplying S minus 9. Are we okay up to that point?
Yes.
Yeah.
Okay, so this is basically what we now have. Now, the denominators will be the same on the left and on the right. So now what we have to focus on is going to be the numerators. So since the denominators are the same, the numerators must also be the same. So we can just get the numerators. So when we get the numerator for the left-hand side, this has to be equal to the numerator on the right-hand side. Now we have to solve this to find what A is, B is, C is, and what D is. To find A, B, C, D, this is where you use trial and error. So you can take S is equals to 0. Yes, please?
What has happened to the denominators here?
Notice that the denominators are the same. So you can say they've cancelled out. It's
all right.
So we now want to find A, B, C, D. To find them, we'll use values of S. Say S is equals to 1, or we start with 0. See, S can take any value. S is a variable here. It can take any value. Say S is equals to 0. What would be A, B, C, D? S is equals to 1. What would be A, B, C, D? You can play through different values of S. But if you just pick them randomly, it might take you longer. You might have to start solving simultaneous equations, and that might be too tricky. However, you can pick them strategically. Take, for example, if you picked S to be equals to 0. You know if S is 0, every term where S is multiplying will be 0. So this whole thing will be 0, eliminating you from working with A, one unknown gone. This does not have S multiplying, so this term will still be present. But here, S is multiplying, so this term will be 0. Here, S is multiplying, this term will be 0. Notice that picking S is equals to 0 allows you to only deal with D as an unknown. So you'll be able to figure out what D is. Not D, B is. Do you see that? So if S is equals to 0, substitute 0 everywhere where there's S in the equation above there. So what are we going to have? 12 will multiply S squared. So S is 0, so that will be 0. Then minus S to the power 3, that will be 0 as well. So on the left side, only 5 will remain. This term, when you put S, will all be 0. The second term here, it will survive, we'll have B. And then this will be 0 minus 9. And then this will be 0 minus 1. This term will be 0, and this term will be 0 as well. So now we'll have 5. This will be minus 9 multiplying minus 1. So we'll just get 9B. Implying that B is equals to 9 over 5. In the same way, let's pick S is equals to 1. You see, you can pick S to be anything. If you want, you can even say 10. Pardon?
5 over 9.
Oh, 5 over 9. Yeah, not 9 over 5. Yes, 5 over 9. You can pick S to be anything, but you don't want to just pick S randomly. If you can help it, be clever about it. Pick a value of S that allows you to find something. Here, for example, why am I choosing 1? I see that if S is 1, this part will be 1 minus 1, which is 0. That will mean that this term will be 0. I won't have to work with A as a variable. This part also has S minus 1, so this part will also be 0. I won't have to work with B. This part also has S minus 1. This will also be 0. I won't have to work with C, leaving me with only one unknown, D. So this choice of S allows me to find D without having to struggle. That is why this is the best choice. So when I put 1 where there's S, 12, S squared becomes 12, minus S to the power 3 becomes 1, plus 5. On the right side, the first term is 0, second term is 0, third term is 0, and then we'll have D multiplying S squared, so that will just be 1, then 1 minus 9. 12 minus 1 is 11. 11 plus 5 is 16. 1 minus 9 is minus 8. Divide both sides by minus 8, we get d is equals to minus 2. So we end up with d is equals to minus 2. Now, based on this, can you look at these expressions? We have so far been able to find b and d. What choice of s can we make here so that we are able to find something here again?
F equal to 9.
Yes, s is equals to 9. If s is 9, this part here will be 0. If this part is 0, we don't have to deal with a. There's 9 here as well. There's s minus 9 here. So if that is 0, this part will be 0. This term doesn't have s minus 9, so that part survives. This has s minus 9. This part will be 0. So s minus 9, oh no, s is equals to 9 is another good choice here. If you pick that, the left-hand side will be 12s squared. 9 squared is 81. Minus 9 to the power 3. What would be 9 to the power 3?
$729.
729.
Yeah, 729.
Okay. On the right side, the first term is 0 because 9 minus 9 will be 0. The second term will be 0 again for the same reason there. The third term will survive. The fourth term will be 0. So from the third term, we'll have c 9 squared, s squared there. That's 9 squared. That's 81. And then s minus 1. So it will be 9 minus 1. So we have 12. Can keep it like this. We can simplify. 12 by 81 and minus 729 plus 5. And then on the right side, we have 81 by 8. So
to give you 648 on the other side.
648 on the right side. And then on the left side,
Okay.
240, 48. Okay. So we have found C, we found D, we found B. The only thing missing here is A. Finding A is a little bit tricky because here there's no right choice that we can pick that will allow us to only deal with A. So since we can't pick a value of S that allows us to only deal with A on its own. So here now we can pick any value of S. So which choice is going to be best? There's no choice here which will allow us to only work with A. Meaning whichever choice we pick here, if we want to find A, we must pick a number that won't eliminate anything here. So what choice can you pick here?
Number that won't eliminate anything.
Yes, because if you pick the one, pardon?
Both 3.
Yes, you can pick 3. Just any number here will work.
Eliminate anything.
Yes.
Even if yeah.
The only condition or just the rule of thumb here, you want to pick a small number because small numbers are easy to work with. 3 is a small number, good enough, but even better, there is 2. You get that right? Okay, so we go with 3 or we go to n or wait?
I will go with 2. Small number.
So let's go with 2. So now, everywhere where there's S, we'll put 2. The best thing about this is we've already found A, B, C, D. Not A, B. We've already found B, C, D. So even if they'll survive here, we'll just put their values there and we'll find them. So let's start with where there's S, we're putting 2. So that's 12S squared. That is 2 squared, which is 4. Then you have minus S to the power 3, that is 8. Then you have S, so that is 2. Then we have S minus 9, that's 2 minus 9. Then that's 2 minus 1. Then that is B. S minus 9, that's 2 minus 9. Then 2 minus 1. That is 2 squared, that is 4C. 2 minus 1. And then that is D. S squared, that's 2 squared, that's 4. D. And then 2 minus 9. Now we'll just simplify this and substitute. 12 by 4, that's 48. Minus 8 plus 5. We can actually simplify this. Minus 8, that's 40. So we have 45 here. This is minus 7. This is 1. This is minus 14. Now we have B here. Minus 7. So you get minus 7B. So again, this is minus 7. This is 1. Minus 7. Minus 7B. Then here, this is 1, so you have plus 4C. Here you have minus 7. Minus 7 by 4, we get minus 28. Is that okay? Are we okay there? Okay. So now substitute for B, C, and D. B, we had what? 5/9. C, we had what? 248 over 648. D, we had minus 2. And then we simplify. So we have 45. In fact, you can take the minus 14 to the other side. Becomes positive 14A. Then you have minus 45. Minus 7 in that, it will be minus 35. And then we'll have plus. Can 4 go into this? So let's just simplify this and see what we get.
Yeah, going to 648 is 162.
162. This becomes positive. Then this will be 56. So we now need to combine this into a single fraction. So after getting the single fraction, you can divide both sides by 14 and simplify. So you have this over 81 by 14. What would be the simplified fraction?
0.6.
As a fraction. It's giving you 0.6 exact?
Giving 0.6 something something.
Oh, so give it as a fraction.
Put it to a fraction, and my calculator is refusing. Fifty over 81.
50 over 81. So this becomes our A. So we can now go back to our partial fractions. We said our ys would take this form. In partial fraction form, our ys was going to take this form. But now we know what A is. A is 50 over 81. We know what B is. B is 5 over 9. We know what C is. C is 248 over 648. This can be simplified as well. What do we get when we simplify this?
Like 1 over 81.
So C is 31 over 81. And finally, D. D, we have -2. So the negative, we'll make the sign here to change to minus. And then we'll put a 2 here. So this is our ys. This is our transform, our Laplace transform. Now, remember, when getting a transform, ys, this is a transform of some function y. Now, having found it, if we wanted to get y itself, which is the solution we want, yt, to get the solution y, we now need to get the inverse of the Laplace transform. That's what we need to get. So, when getting the inverse in this case, it is very straightforward. So all we have to think about is what expression. Remember, like when I said, what is the Laplace transform when we were solving earlier of t? If you recall, for t, the Laplace transform was just 1 over s squared. What does this mean? If now we find 5 over 9 over s squared, we can look at it as 5 over 9 multiplying 1 over s squared. So since this is the Laplace transform, its inverse, it means where it came from. It must have come from t. That must have originally been a t, so that its transform was 1 over s squared. So that's how we're doing this. Again, you're seeing the need of you mastering the transforms. So here we're seeing this one is going to be 5 over 9 multiplying t. That's this one. In the same way, this one here, this one can be viewed as 50 over 81. Yes? There's a question?
Yeah, I have a question. Just go back a bit.
Up?
After calculating 50 over 81,
Yes.
you had to go and just replace those values into the equation?
Yes, remember that we were trying to get the partial fractions. And these are the partial fractions. We said since we have a repeating factor, linear factor, from the repeating factor, we'll have two fractions. From the linear factors, we'll have these as well. So under partial fractions, we're saying this expression for ys can be written like this. That's what we're saying. It can be written like this. We just need to know what A is, B is, C is, and D is. So having found A, B, C, D, we just replace them here.
Okay, great. Okay.
Now, after replacing, we're now saying the solutions we have found here, they were transformed from some function yt. We now want to reverse that process. We're getting the inverse of these transforms. The example I gave you was for 1 over s squared. We recall that earlier, when we got the Laplace transform for t, we said it was going to be 1 over s squared. So the inverse of 1 over s squared has to be t. So the inverse of 1 over s squared here is just going to be t. In the same way, this term here, 50 over 81 over s, we can view it as 50 over 81 multiplying 1 over s. Now, we want to get the inverse, meaning what must have been the function such that its transform reduced to 1 over s. So in this case, notice that it's in the series of t to the power n. The only difference is that you kind of have to know these transforms. You really, really have to know these transforms. If you have t to the power 1, pardon?
So,
Pardon?
it has to be t to the power or something.
Exactly. It has to be t to the power 0. And t to the power 0 is 1. Meaning that this will just be 50 over 81. T to the power 0 will just be 1. So we'll not write that t to the power 0. Have you got that?
Yes.
In the same way, what is the inverse for this one? That is now 31 over 81 multiplying 1 over s minus 9. Again, what function did we transform to end up with this? Any ideas?
I think it has to be t to the power.
Now, this is not t anymore. This
Yeah.
is not t anymore. The ones that deal with t to the power, the ones that deal with t to the power n, these are always going to be 1 over s to the power n plus 1. Remember this?
Yes.
So when you look at the expression we have here, this is s minus 9. It is not in this form. So its inverse cannot be t to the power anything. So this one is going to be for an exponent. You have to recall these. Yeah, remember you have to know for an exponent, for a sine, for cosine, and so on. So we had actually derived these transforms. Let me just show you. When we had for s, so here we had, this was for sine. Did you do for exponent? I think we did for exponent as well. When f of t is an exponent, yes. Notice that the transform reduced to, where is that here? You see that?
Yes. 1 over s.
1 over s minus alpha. And do you see where alpha is? Alpha comes here. So in our current expression, what we have is 1 over what? S minus what? 9.
9.
So meaning it must have come from f of t is equals to what? E to the power 90, yes.
90.
Yeah. So again, it requires you to know these transforms in case they're not given to you. So this one, you're going to have plus 31 over 81, and then e to the power 90. And then see that the last one also has the same shape, right?
Yes,
The
yes.
difference is only a minus here. So what are we going to write?
I think it should be 2 times e to the power negative t.
Negative.
Is it possible?
Remember here we had minus 9. We didn't write minus 9.
Yeah, to the power t, so.
The power t, yes.
I remember there was one thing that was changing. I've forgotten, I just need to go through. There's one formula that was changing. If it is s minus 9, when you're taking it up there, inverse it would be plus.
So the formula is 1
So
over
that's what we say.
s minus alpha. This is what you get if you have f of t is equals to e to the power alpha t. Meaning, if what you have is 1 over s plus 4, then you're going to have e to the power minus 4t.
Okay, yes, that's the one that I was trying to think of.
Yes. So this is how we use the transforms to solve a differential equation. Notice that they're not hard. They're just long. And they require you to remember the transforms.
And it's just one